Hello, this is video 26. In this video, I'm going to continue going over Newton's second law problems. This time, they'll be dealing with what is called apparent weights. So apparent weight is the sensation of weight due to contact forces supporting you. I'm sure you've been in an elevator, and sometimes you just feel different when the elevator is accelerating upward or downward very quickly. So you've probably felt that when you're accelerating upward, that you just feel heavier. But if you're accelerating downward, you feel very light. You get that weird sensation in your stomach that just makes you feel different. So that's your sensation of your weight. Your real weight hasn't changed, but what's happening is that the floor is pushing at you that normal force. It's a different normal force depending on which way the elevator is going. And that normal force from the floor pushing on you is what gives you that sensation of weight that is different sometimes from your regular weight. So let's look at these three cases and figure out what is your apparent weight if the floor of the elevator is accelerating upward or downward, as in the case in an elevator. And we can also do the case where the elevator is not moving. So I'm actually going to do these in the next slides. So I have plenty of room. So the first case is not moving. So what we need to do is we need to draw a free body diagram for the person. So there's going to be a weight going down and a normal force going up. And that normal force is going to be the apparent weight. That we can also call it W sub A, your apparent weight. That's what makes you feel your certain weights. So the forces are vertical. We'll do the sum of the forces in the y equals MAY. But since we're not moving, we're in equilibrium, we'll simplify that to 0. And then we're going to add up the forces that we drew. So WA minus W, since upward is positive and downward is negative, equals 0. So that means that your apparent weight equals your weights, which is mg. I could have substituted mg right here. And that's what you expect. You feel your regular weight when the elevator is not moving. Now what about if the elevator is accelerating upward? So your free body diagram, it actually doesn't change. You still have your weights pulling you down and your apparent weight of the floor pushing you upward. Now please note that I'm not drawing the forces to scale. Technically, if I were to draw them to scale, you'll see that I'd have to draw the apparent weight bigger than the weight. How do we know? Well, let's take a look at Newton's second law. The sum of the forces in the y equals MAY, which equals 0 because, it's not equal to 0 in this case because we are accelerating. So you see, don't get so used to just keep on crossing this equal to 0. If you're accelerating, then you're not in equilibrium. And now go ahead and sum up the forces that you drew. So WA minus W equals MAY. And since there's only one acceleration and it's vertical, I can just call it A. I don't have to call it AY because everybody knows which way the acceleration is. So I can replace the weight with mg, so WA minus mg equals MA, and then solve for WA, the apparent weight, equals mg plus MA. So you can see that this explains why we feel heavier when the elevator is accelerating upward, because we feel mg plus MA, which is more than mg. So technically, when you draw free body diagrams, that if one force is bigger than another, it should be drawn bigger. I tend to not be very picky about that, but just in case you have a question that has a choice where it had WA equal to W and had WA bigger, and if it was drawn bigger, you would want to pick that option. Then the last case that we were doing is the elevator is accelerating downward. Once again, the free body diagram doesn't change as far as the forces, but it does turn out this time that the weight will be bigger than the apparent weight. Now, if you don't know that, if you draw the forces in the same length, that's okay. I'm not too picky about that. Just know eventually which one is bigger than the other. So this is where it gets tricky. So I'm going to separate this. I'm actually going to do this example two different ways. The first way is the way that we've been choosing our coordinate system, with up being positive and down being negative. So when we do this and we write down Newton's second law, the sum of Fy equals may. I'll just write ma, there's only one acceleration. If we do this, we have to be very, very careful when we put in our numbers, because we're going to have wa minus w as before, but now a is going down, it's negative. So it's equal to m times negative a, which is negative ma. And so many students that I've seen, they forget to put that negative here. So when you solve for WA, you're going to get W minus MA or MG minus MA. So we can see that you feel lighter when it's accelerating downward. Your apparent weight is MG minus MA. So personally, I don't like using this coordinate system just because I've seen so many students forget that negative. So what I like to do when I solve this problem is I like to change my coordinate system. A lot of you guys are not going to like this right away, but I think it will grow and you'll start liking it eventually. I like to think of whichever way the acceleration is going to be my positive direction. So for this particular case, I would say down is positive, up is negative, simply because I'm looking at the direction of the acceleration. So now when I write Newton's second law and I sum up my forces, I'm going to look at the ones that are going in the same direction as the acceleration, which is the weight. So the weight minus WA equals MA. And A is positive because of my coordinate system, so I don't have to forget a negative here. And now when I solve for WA, you can see if you add WA to both sides, subtract MA, or if you subtract W and then multiply by -1, you'll see that you're going to get WA equals MG minus MA, W minus MA, just like before. You haven't changed the problem. All we've done is change the coordinate system. The reason I like to do this is so that you don't forget this negative here that so many people forget. It might be weird to call down positive and up negative, but if you just think of it as whichever way the acceleration is going to be positive, it makes it easier. But again, you can choose whichever method that you want. So just to recap, when we're solving Newton's second law problems, we're always going to ask ourselves if we're in equilibrium, and in this case, when we weren't in equilibrium, then being in an elevator, accelerating upward or downward, changed the sensation of our weight, which we called our apparent weight. I actually have another question here, so let's not, that was already a recap, but let's finish up here. So you ride in an elevator that is moving upward at a constant speed. How does your apparent weight compare to your true weight? So you may see, oh, well, I see upwards, so that means I feel heavier. But don't make that mistake. Your apparent weight is going to be the same because the key word is constant speed. Constant speed, whenever you see that, you want to think equilibrium. That word needs to pop into your head. And that means that the two forces will balance in this case. This is the same as if the elevator was at rest. Now, if the elevator was accelerating upward, that's when your apparent weight would be larger than your true weight, as we just saw in the previous slide. And I actually have one more question here. This question is actually just to introduce a little topic. I didn't want to make a big deal out of it, but I did want to mention it, so I thought the best way was using a your turn question. So it says, which of the following is true about a person in free fall? So again, you may not know this, but again, the purpose of this question is just to introduce this little topic here. So when you're in free fall, you feel weightless, all right? But that doesn't mean that you have no weight. You're not going to lose your weight just because you're falling. So the correct answer is actually D, that both B and C are true. You're weightless and you have zero apparent weight. So the reason I have this slide is to let you know that weightless does not mean no weight. They're two different things. Weightless means that you don't feel any apparent weight. So it means what choice C is saying. These two things mean the same thing. I like to bring this up because when you have astronauts in outer space, people usually say that they're weightless up in outer space. That doesn't mean that they don't have any weight. It just means that they're actually in free fall. They have no support force pushing them upwards, so they feel like they don't have any weight, but they still have weight. That's the end of this video. I've already recapped it, so I hope it was helpful to you.